Okay, so last lecture when I actually teach you new stuff. So actually I'm going to put this thing in front of the screen so I can't see it. It is recording, good. Okay, so today we're going to cover network flows, which sometimes algorithms courses don't get to. And so in the fall I didn't actually get to this because people kept stopping me and asking me questions, but that hasn't happened so much, and actually not at all since I started doing these things offline. So we have time for it. One lecture, woohoo. So it's quite cool. Network flows. So the idea is quite simple. Well, the problem is quite simple, the basic problem. And it lets me use an example from the textbook, which is Canadian, woohoo! So there is this problem about the Lucky Puck Company. They've flown, the Lucky Puck Company has a factory, which is a source in Vancouver that manufactures hockey pucks, and it has a warehouse, which is a sink, in Winnipeg that stocks them. Lucky Puck leases space on trucks from another firm to ship the pucks from the factory to the warehouse. Because the trucks travel over specified routes between cities and have a limited capacity, Lucky Puck can ship at most CUV crates per day between each pair of cities U and V in figure 27.1a. Lucky Puck has no control over these routes and capacities and so cannot alter the flow network shown in 27.1a. Their goal is to determine the largest number P of crates per day that can be shipped, and then to produce this amount, since there is no point in producing more pucks than they can ship to their warehouse. The rate at which pucks are shipped along any truck route is a flow. The pucks emanate from the factory at the rate of P crates per day, and P crates must arrive at the warehouse per day. Lucky Puck is not concerned with how long it takes for a given puck to get from the factory to the warehouse. They care only that P crates per day leave the factory and P crates per day arrive at the warehouse. The capacity constraints are given by the restriction of the flow FUV from city U to city V to be at most CUV crates per day. In a steady state, the rate at which pucks enter an intermediate city in the shipping network must equal the rate at which they leave, otherwise they would pile up. Flow conservation is therefore obeyed, thus the maximum flow in the network determines the maximum number P of crates per day that can be shipped. Okay, what does all that mean? So, the problem is, we have this map of cities, and you have the factory here. A source is where stuff is produced. Okay, simple enough. A sink is where stuff is consumed or stored in a warehouse. And you're allowed, the numbers on the edges are the capacities. You're allowed to send that much stuff down each edge. But at the vertices, you have this, if you've done like circuits and stuff like that, you should have done Kirchhoff's laws, which say, okay, like the flow in, the voltage in is the voltage out. Is that right? Is it voltage? It's been so long. Anyway, flow in is, in my language, flow in is flow out, you know, in computer science, right? So if you have like 3 units of whatever, crates of pucks entering Regina at, then you must have a total of 3 leaving, okay? Okay, how do you get what is the most stuff you can get from S to T? Well, pretty clearly, you could come up and you could say, okay, what I'm gonna do is I'm gonna ship 12 crates from Vancouver to Edmonton, and from Edmonton to Saskatoon, I'm gonna ship 12 crates, and I'm going to ship 12 crates from Saskatoon to Winnipeg, and I'm going to ship 4 crates from Vancouver to Calgary, and 4 crates from Calgary to Regina, and 4 crates from Regina to Winnipeg. Okay, so that's fine. You're obeying all of these capacity constraints, and the sum coming into every vertex except the source and the sink. The sum coming in is equal to the sum going out, so we're all happy, and we get 16. Okay, is that the best? So how we usually write this is 12 out of 16, 12 out of 12, 12 out of 20, 4 out of 4, 4 out of 14, 4 out of 13. Can we do better? Well, that's what this lesson is about. How to find a maximum flow. Okay, so this is a very simple example. Probably you could find a maximum flow by yourselves just by looking at it, but we're going to do the algorithm to try to improve this. So what we have, we have this flow. So we construct another flow network, well, another network, which is a flow network, but I don't want it to be confusing. So, but with different edges and capacity, same vertex set. And what this network is, this is called the residual network. And it says how much we can change things, okay? So we have 12 out of 16 going from Vancouver to Edmonton. So that means we could add another 4 pucks, 4 crates of pucks per day. We could ship that from Vancouver to Edmonton. They might not have anywhere to go. They might get stuck there, but you could do it. There is capacity on that edge. There is no capacity on the edge going from Edmonton to Saskatoon. There is capacity 9 going from Vancouver to Calgary. There is capacity 10 going from Calgary to Regina. There is no capacity going from Regina to Winnipeg. There is capacity 7. There is capacity 10 and 4 and 9 and 8. Okay, are we done? No, we're not done. Okay, so we've drawn all the edges that are not at, all the edges from here that are not already full, that are not already carrying pucks to their capacity, but we can still change things the other way. So that means we are shipping 12 crates of pucks per day from Vancouver to Edmonton. What could we do? We could change things by shipping fewer crates of pucks. So we can add 4, or we can subtract 12, right? So how do you draw this possibility to subtract? Well, you draw it by putting an edge in the other direction, okay? So this becomes, we could, instead of shipping 12 from Edmonton to Saskatoon, to say that we could reduce that, we draw an edge going backwards. Okay, so this is 12, this is 12. Here, we can reduce, actually let's put this 10 up here so that we can draw this, and we can say we can reduce this by 4. We can reduce this by 4. We can reduce this, let's put this 9 on this side, by 4. Okay, is there anything else? Yeah, we can reduce this by 12. So, now is that it? Okay? So, now we have the residual graph, the residual network. And the question is, from this, can we somehow find a way to add more flow to this? And the way that you think about adding more flow is if you can get from S to T, if there is a path from S to T, that means that there are edges where you could send more pucks. If there is some path, then you could send, so it's going to have, with positive capacity, then you could send more pucks along that path. So you could add that to this flow and get more pucks per day shipped from Vancouver to Winnipeg. Yay, hockey, yay. Woo. Okay, so is there a path from S to T? Yes, there is. Look. We can send 4. Wow, okay, forget about how much we send. But we can get there, okay? So it goes 4 and 10 and 10 and 7 and 8. So how much do you send? Actually, I forget. It seems like something I might have taught in the fall. Maybe I did get to network flows. I forget. But how much could you actually send along that path? Well, it's going to be the minimum capacity of any edge along that path, which is, so the minimum of 4 and 10 and 10 and 7 and 8 is 4. So we're going to add 4 here. And then we're going to add 4 going this way. And then we're going to add 4 going this way. And then we're going to add 4 going like this. And then we're going to add 4 here. Okay, so now we don't get, okay, so now I'm going to draw this. Now we have 16, 12. Okay, so 16 out of 16. 12 out of 12. 16 out of 20. 4 out of 7. 4 out of 4. 4 out of 13. 4 out of 10. So notice now I'm drawing the edges in there, and then this is 8 out of 14. So now, and then here it's 0 out of 4, and that's the only other edge. So we're not using this edge at all. This is 0, not a 6. So let's see, out of wait, something's gone wrong here. No, that's okay. Sorry. So coming out of here we have 20. Coming in here we have 20. Coming in here we have 16, and leaving we have 4 and 12, which is 16. Coming in here we have 4 and 4, which is 8, and leaving we have 8. Coming in we have 8, and leaving we have 4 plus 4, which is 8. Coming in we have 12, plus 4, which is 16, and leaving we have 16. So we're still obeying this flow in is flow out. The outflow from the source is equal to the inflow to the sink. Nothing is going over capacity, and now we have 20. We have a flow of 20, which is better than our flow of 16 that we had before. So we are happier. Are we optimally happy? Well, maybe, but let's find out. If we can find the recipe. So once again, we draw a residual graph. I'm going to be so happy. Oh, actually turn this light on. Maybe that's a bit better. I'm going to get my coffee table back. That's what this camera is standing on. I have a jigsaw puzzle, and I haven't been able to build the jigsaw puzzle because I was doing it on I have nothing else to put it on. So let's build the residual network again. Here, the only thing we can do is we can't increase the flow across this edge anymore. We can only decrease it. So now we can increase this one by 9, or we can decrease it by 4. And we can increase this by 6, or we can decrease it by 4. And actually, we can decrease it by 8, I believe. Yes. So I think it's 8 because you could reduce it by these 4, and then you could stop sending these 4 across, and then you could start sending 4 back from Calgary to Edmonton. So you could increase this by 6, you can increase this by 8. You could increase this by 6, or you could stop sending these 8 over. Okay, so you could increase this by 3, or you could decrease it by 4. So you can't increase it across this edge going from Edmonton to Saskatoon, but you can decrease it by 12. So you send 12 fewer from Edmonton to Saskatoon, which is effectively like sending 12 more from Saskatoon to Edmonton. This confuses a lot of people. Just go with it. It's probably, I mean, I could try to explain it, but it's probably easiest like at the end of the course. Just like get used to it and just accept it. Like, I mean, you can, it's talking about Kirchhoff's laws. I mean, if you think about electricity, when you can think about like positive charge flowing one way or negative, actually, the story about Benjamin Franklin, and he had like a 50% chance to decide which way stuff was flowing, and he decided wrong. That's the story I heard. So it's because he decided stuff was flowing from positive to negative. It's like, no, it's not. Actually, stuff flows from negative to positive. That's why it's kind of backwards. Okay, so this this can go 4 like this. This could increase by 4, or it could decrease by 16. Okay, is this everything? 9. Yes, yes. Okay, so now, is there a path? Yes. Okay. So can we find, now this is called an augmenting path. Okay. So it's these fancy terms. Does the residual, not residual network contain augmenting path, well, actually, I guess in the residual network, the augmenting path is just a path from S to T, but okay. Okay, you've already seen assignment 6, so you know I don't actually ask you about this, I think. Okay, so where, well, can you get from S to T? And the answer is yes. You can go here, and here, and here, and here, right? So there is a path from S to T. What is the minimum capacity along that path? It's 3. So what are we going to do? We're going to take this, and we're going to add 3 here, and we're going to add 3 here, and then we're going to add 3 here, and we're going to add 3 here. Okay? Cool. So this is going to be, well, I'm just going to do it with it. So this is going to be 7. This is going to be 11. This is going to be 7. And this is going to be 19. So now we've gone from first we had a flow of 16, then we got a flow of 20, and now we have a flow of 23. And I could draw, well, yes, I will draw. Okay, it's not super useful, but I'm going to draw the residual graph just so you can see what happens next. So we have this. So we can increase this by 6, we can decrease it by 7, we can only decrease this by 16, we can only decrease this by 12, we can increase this by 6, or decrease it by 8. So we didn't do anything. We can increase this by 3, we can decrease it by 11. We can only decrease this by 7. We can increase this by 1. Let's put the 1 on this side. We can decrease it by 19. And we can decrease this by 4. Oh, rats! I've been forgetting to put this 9 in sometimes. Okay, but it doesn't, does it change anything? And we can increase this by 9. Does that... no, that actually, I don't think that changes anything. So, is there a path from S to T? Does the residual network contain an augmenting path? No, right? Because you can get here, but you can't cross this edge. You can get here, and then you can get here, but you can't cross this edge. Right? You can get here, but then you can't get anywhere from here. So if you actually look at it, you can get to this vertex, from this vertex you can get to this vertex, and this vertex, but you can't get here. Right? So you can't get to either of these. So there's actually, this is called a cut. Right? There are no edges going that way across that red line, the cut. So no, there is no augmenting path. So actually, you could see that by looking at these three edges. Oh yeah, I've got this. I forgot to draw this line. 0, 9. If you look at these four edges, right? So this is going to be a blue cut. These edges, there's nothing going this way in the residual graph, so that means that all of the edges that go across this cut from left to right are already at capacity. Okay, so you can't push more flow across that cut. And this leads us to something called the max flow min cut theorem, which is the maximum flow from S to T in a network is equal to the size of the minimum cut, where you can take the edges and slice them, and you say, okay, going from the part with S to the part with T, what is the capacity of the edges that go that direction across the cut? And it says, okay, the maximum flow obtainable in the network is equal to the sums of capacity of the edges going the right way across that cut, across the minimum sum, the sum across the minimum cut. Right. So let's just pause while I erase the board. So okay. So, okay, this is how you find a maximum flow. In particular, this is how you're supposed to answer the question on the assignment if you can't just sort of figure it out by like eyeballing it. What you should do is just start with a graph, and maybe you have a flow of 0, build a residual graph, find an augmenting path, which is a path from S to T in the residual graph, and then add the augmenting path to your flow, build the residual graph again, build a new residual graph, find an augmenting path, and keep doing this until eventually you stop. Now, there is a small problem with this, which is this is in the book, by the way. So more than I'm going to tell you, it's in the book, and it's online, and so there are no huge surprises. So if you really find this stuff fascinating, you can find out more. The problem is if you do this carelessly, what you can have is you have S, and you have a capacity of 1,000,000 and a capacity of 1,000,000. And I think you have, this is also in the book, I think. I think you have one going one way and one going the other way. So what you get if you start with okay, if you build the residual graph, which is going to be, am I switching accidentally between red and okay, so you build the residual graph, which is actually this. And then you say, okay, I find a path. I'm going to put 1, so that the path I find is this. Okay? Then, which is silly. Okay, I'm going to go here. This is a path. It's not, I mean, it's not a very good path, but so now I'm going to get do I need two edges here? What can I do with just one? And maybe I can do it with just one. What happens if I erase this one? So I still find this path from going from up here down here. And now there is, yeah, okay. So now this edge isn't here in the residual graph, but this has 99999 capacity in the residual graph. This has 1,000,000. And then now, because it's the residual graph, this I can reduce the flow across. So I have, okay, so what I've got is a flow of 1 out of 1,000,000, and then 1 out of 1, 0 out of 1,000,000, 0 out of 1,000,000, and 0 out of 1,000,000. Oh no, sorry, this is 1 out of 1,000,000. Okay, so I chose this augmenting path, so now my flow is 1, 1, 1, and everything, and on these two edges the flow is 0. So now I build the residual network, which is the residue here is 999,999. The residue here, I can reduce the flow across this edge by 1. So instead of going down, now it goes up. This is 1,000,000. Oh yeah, I have 1. I can reduce the flow across this edge by 1. And I can reduce the flow across this edge by 1, and I can increase the flow across here by 999,999. Okay? So now, that's my new residual network. Can I find a path? Yes, I can. Sorry for my inconsistency with colors. I could find a path like this, but I could be unlucky or silly or something and find this path, which now increases. So what's the minimum flow along this path? Well, it's 1. So I'm going to take plus 1. This is actually going to be plus 1 in this direction, so it's going to cancel this one. And then it's going to be plus 1 here. So I'm going to get a new flow, which looks like this, which is 1 out of 1,000,000. And 1 out of 1,000,000. And this edge is 0 out of 1. And this is 1 out of 1,000,000. And this is 1 out of 1,000,000. So you see, if you choose your augmenting path badly, you could always choose. So if you draw your augmenting path now, you could next time you could go, oh, like this, add 1 here, add 1 here, add 1 here, and then you could so now you'll have 2 and 1 and 2 here, and 1 and 1 here. And then you say, oh, but then I can find an augmenting path that goes like this and like this and like this. So now this goes back to 0, and this goes 2 and 2. So you'll have 2 and 2 and 2 and 2. So you can actually do that. How many times do you have to iterate this before it actually hits the maximum flow? But 1,000,000 or 2,000,000 times do you have to do this? Anyway, a lot. I guess it's probably 2,000,000. So this is if you find your augmenting path badly. Um, oh, so what I should mention is that this whole approach is called there are other ways to find maximum flows, and they're in the book, but we're not going to talk about them. They're a bit faster. They can be faster. So this is this general approach is called Ford-Fulkerson. So the approach is find augmenting path in the residual graph, residual network. And this Ford-Fulkerson, however you do this, and then if you find and as you can see, that can take a long time. And then there's a variation, well, an implementation of this, which is called Edmonds Karp. Which is find shortest augmenting path. In the residual network. So if you do that, I believe this takes O of size of V times size of E squared time. So cute thing. I think I mentioned before that there aren't. I mean, how many people are there in computer science? A lot. How many people's names keep coming up? Not that many, because so you saw Kolmogorov came up when we talked about Karasuba, and then we came up again when we talked about Kolmogorov complexity. Cooked came up in Karasuba for Toom-Cook, and then Cook's theorem. Karp came up when we talked about Cook's theorem, because Karp was the one who showed that all of those problems like clique and the 21, I think, clique and hitting set and hand path and stuff. Karp showed that those were NP complete. Well, and then he came up again in Karp-Rabin, the pattern matching algorithm that I talked about in the last lecture. And look, it's Karp. You just can't get away from the person. Edmonds is, I believe, Jack Edmonds, who was at Waterloo for a while. I don't know where he is now. But his son, Jeff Edmonds, is a professor at York University in Toronto, and did his PhD, I think, with my master's supervisor in the same department with Cook. And my master's supervisor did her, I think she did her PhD with Karp. And so Ford-Fulkerson, I don't think Fulkerson's come up before, but in Bellman-Ford, it's the same Ford. You don't have to remember that many names. This makes life easy for you. Although it does make it a bit harder if somebody says, so-and-so's theorem, and you think, yeah, which one? If somebody says Euler's theorem or something, he had many. So, now I'm going to take a break and erase the board, and I'll pause while I'm doing that. And then we're going to cover the max flow min-cut theorem. And going to show you some applications of this. So, okay, how much time do I have? Okay, so that was 40 minutes. So I'm going to stop it here. And no, I'll stop it here. And then we can have a second part. And I'll come back and do max flow min cut and maximum matchings in bipartite graphs. And yeah, I mean, I could show you why this is true, but I'm not going to, because I have like 40 minutes. Maybe I will at the end if I have time. And some applications. So obviously you can use this stuff to find maximum flows, but you can actually also use it to find stuff that doesn't look like maximum flows. So one group I worked with, they love this stuff. We did path covers, and you do minimum path covers in DAGs with so a guy called Alex Tomascu is sort of my tame flow expert. Also, I got Romeo Rizzi. So if I have problems with flows, I ask them. Right. Okay, that's enough babbling. Okay, see you in a few minutes. Okay, wait. No, I just paused it. I meant to actually stop it. Oops.